Well, hello YouTube, it's me, Fortmaster, and it's another overly sarcastic productions reaction today, and yeah, I don't know what category to put this in, because this is just simply called Space Did Something Cool. I mean, what can you say about something so vague? I mean, I don't know what they're talking about. I mean, there's a lot of cool things in space. There's a reason I watch videos on, like, Kutzkazard and stuff like that. What does the description say? Red takes the week in a very weird direction to talk about what she got up to in October. It's space. It's always space. It's very likely that the thing Red is enthused about has something to do with space. Okay. I mean, sign me up. Let's see what this has to do. So yeah, of course, as usual, original video is linked in the description if you haven't seen it for some reason. Corner video will lead to my Let's Play of the day, and with all that out of the way, let's actually get this thing started then, shall we? Oh, hey!
There's the myth. There's supposed to be an earth-shattering myth.
Exactly!
All right, I'm gonna level with you. Sometimes when there's a specific bit I want to do, I'll go looking for myths and folktales and stories that I could retell that would help justify me talking about it. And this time, I wanted to talk about solar eclipses. Specifically, this solar eclipse that just happened on October 14th, 2023. I thought it'd be easy to find a framing device, but I came up surprisingly empty in the myths department. Like, for all the talk of solar deities imperiled by snakes or contentious relationships between the sun and the moon, there weren't really any specific legends that were jumping out at me for a retelling, which, when I thought about it, made sense. Solar eclipses are historical events, albeit rare ones, and while myths can be shaped by history, they don't tend to actually correlate to it one-to-one. Mythology usually turns historical events into themes or threats or object lessons, like how the Minoan eruption probably shaped Plato's narrative of Atlantis. So when it comes to solar eclipses, you get myths where the sun is in danger of being snuffed out, but as far as I can tell, you don't really get mythologized stories about a time it happened and what it specifically meant. That would be called a historical account, which
Okay, actually, wait a second. There is... Wait, no, yeah, historical account, because the only thing I can really think of specifically would be... I forget whether it was a siege of Constantinople, or if it was, like, the Byzantines or Romans invading, like, somebody else, but there was something involving, like, the astronomers knew an eclipse was going to happen, and when the moon turned red from it, they used that to, like, scare whoever they were invading or whoever's being invaded. I'm not remembering this very much. Sorry.
As we've discussed previously, is not my department. And then I kind of stepped back and thought about it, and I came to this very crucial conclusion, which is that I can do what I want. I don't need to launder my arguments. I don't need to sell a pitch. I don't need to dig for a myth that would let me justify talking about this thing I want to talk about. I can just talk about the thing. And if you guys don't want to see that, you don't have to watch it. That's the great thing about YouTube. You're not a captive audience.
Exactly.
Talking about what we want to talk about because we're passionate about it is literally the entire mission statement of this channel. So, today, I want to talk about eclipses. First off, here's how they work. An eclipse happens when the sun, moon, and earth are all in a perfect straight line with each other. If the earth is perfectly between the sun and the moon, we get a lunar eclipse where the earth's shadow is cast on the face of the full moon. If the moon is perfectly between the sun and the earth, we get a solar eclipse where the moon covers the face of the sun. Now, if the earth, sun, and moon all moved in perfectly aligned cosmic clockwork with each other, we'd expect to see an eclipse every couple weeks on the new and full moon, because a new moon happens when the moon is between the earth and the sun, and the full moon happens when the moon is at its farthest point away from the sun.
Well, yeah, but that's also the thing. I mean, just because we don't see them doesn't mean they're not happening. I mean, as I said, it's like every few weeks. But you have to also remember, the Earth is mostly covered in water. But I know I don't know a lot of things, but of the few things I do know that the ratio of people living on land to the ratio of people living on the water is vastly skewed in the favor of land.
The sun. And those parameters sound like they're equivalent to the conditions under which an eclipse can occur, the moon being between the earth and the sun, and the earth being between the moon and the sun. But eclipses don't happen that often, for one simple reason. Despite the universe appearing, at first glance, to be a perfect machine of wheels within wheels, on a planetary scale, everything is actually pretty wobbly. So, while the earth orbits the sun and the moon orbits the earth, and they nearly hit hit that alignment every couple weeks, nearly doth not an eclipse make. The
No, it
orbital
does
plane
not.
of the moon is tilted at a 5-degree angle from the orbital plane of the Earth, which is also known as the ecliptic. Which means most of the time, the arc of the moon's path is either going to be slightly above or slightly below the sun from our perspective. And that means
Okay,
even
well,
if the
that I
moon is
didn't know
new,
that.
aka between the Earth and the sun, it's not going to be perfectly aligned between the Earth and the sun, so we don't see any overlap. It's going to be a few degrees above or below it. But because the moon spends half its tilted orbit above the ecliptic and the other half below it, there must be 2 points in that orbit where the moon passes straight through the ecliptic. That's just
Yes.
property of continuous geometry, baby. These points where the orbit of the moon intersects with the orbital plane of the Earth are called lunar nodes, and eclipses can only happen when the lunar nodes intersect with the line defined by the Earth and the sun, which means when the moon is in the lunar nodes at the same time that it is either full or new. The moon is passing through the lunar nodes at all times of year, but usually
yeah.
it'll be when it's a crescent or gibbous or otherwise just not in line with the Earth and the sun.
I know it's an old word, but I mean, the fact, just whenever I hear the word gibbous, the first thing I think of is Team Fortress 2. Do I still have my ghastly gibbous? I'd have to check that. It's been a while since I looked at it. Ha! I still have it! Yes!
Sun. In order for an eclipse to happen, the moon needs to be in one of these 2 perfect intersections of 2 planes and 1 line. But because we're working on the planetary scale, where the objects are very big and the time scale is very slow, this precision is less forbidding than it might sound. The eclipse season happens just shy of every 6 months, more specifically every 173.31 days, and they last between 31 and 37 days, enough for 1 full orbit of the moon plus a little extra. And in that interval, when the lunar nodes are aligned with the Earth and the sun, all we need to make an eclipse is a full moon or a new moon. And since the moon completes an orbit in just about 28 days, conveniently, eclipse season lasts just long enough for at least one of each. When the moon is full, it'll catch the shadow of the Earth and experience a lunar eclipse, and 2 weeks before or after that, the new moon will pass through the Earth-Sun line and cause a solar eclipse. But this might sound like it's not adding up. This means that solar eclipses are happening every 6 months, but most of us have probably never seen more than one, if we've seen one at all.
I've never seen one, but as I said before, most of the planet's covered in water.
How come we aren't seeing them as often as they're happening? Lunar eclipses happening every 6 months isn't as surprising. It about lines up with how often we hear about them on the news, and it's not hard to believe that they really are that common. But there's a key difference between how a lunar eclipse and a solar eclipse work. When the Earth's shadow covers the moon during a lunar eclipse, it's actually darkening the moon's surface, which means that effect is visible from anywhere that can see the moon, which is anywhere on the nighttime side of the Earth. Anyone who can see the moon will see the Earth's shadow slowly cover it until it goes a dim blood red.
Which, again, if you've met or heard of anybody who thinks that the Earth is flat, they somehow think the Earth is flat even with that proof.
Solar eclipses are a lot more finicky. The moon is quite big, but it is a lot smaller than the Earth, so even if it's perfectly in line between the Earth and the sun, the shadow of the moon is not going to be big enough to cover the Earth. In fact, it only covers a small fraction, tracing a path of totality along the Earth's surface before finally sliding off into space again. So solar eclipses may be happening every 6 months, but that doesn't mean they're visible from more than a fraction of the Earth's surface, and usually not for very long. A solar eclipse can be happening, but if you're far enough away from the shadow of the moon, you wouldn't see it. From your perspective, the moon and the sun would not be aligned. And even with all these variables, there's still some more wiggle room, and I mean that literally. The sun, moon, and Earth don't just snap into the same clean arrangement every few months. When we start looking for an arrangement as precise as an eclipse, we really start to see how wobbly and ramshackle the whole cosmic mechanism really is. Everything's orbiting in ellipses at very slightly inclined angles to each other, and everything is wobbly, and the gravity of everything affects everything else, and it's a whole thing. There are a lot of subtly different ways the Earth, moon, and sun can be arranged relative to each other while still having enough of an alignment to produce eclipses. And
which actually, the fun fact, something I only just learned recently. So I think we've all heard of, the tides and, the fact that the tides are affected by the moon. I didn't know that there are apparently also solar tides. I still haven't looked up what they are or like how drastic they are, but it's on my to-do list to do for today, so that's going to be actually pretty cool.
And in that nearly 6-month interval between eclipse seasons, they really just go from one arrangement to another. Some eclipses don't fully cover the sun. Some last a lot less time than others. Some trace paths north-south, while others go the opposite way. It takes a lot longer than one eclipse season for the various orbits to realign into the exact same arrangement they had during a previous eclipse.
Of course.
Well, this interval of time is called a seros, which is exactly 223 lunar months, 38 eclipse seasons, 6,500 1,585.321 days, or just over 18 years. The Saros interval
wonderful.
is crucial in understanding and calculating eclipses, to the point that it was actually built into the Antikythera mechanism specifically for the purposes of predicting lunar and solar eclipses, down to the day and the time. After one Saros interval, the Earth, Moon, and Sun will be back into almost exactly the same position they were before, and it will produce an eclipse that looks very similar to the one that happened one Saros ago. These are called Saros series. But even then, did you notice that 0.321 days? The Saros interval is not a whole number of days, and that means that even if the same kind of eclipse recurs 18 years later,
it's going to be in a slightly different place than it was before. Oh, joy!
it'll be 8 hours later in the day, which is a full third of the Earth's rotation. So the moon's shadow may be being cast on the same place, but the Earth has turned out from under it, and a different part of the Earth is seeing that eclipse. The bottom line is, that solar eclipse might look the same as the one from one Saros ago, but it won't be visible from the same part of the Earth. One more factor that makes this complicated is the subtle variation in the distance between the Earth and the moon. The moon's orbit is very close to circular, but it's not quite perfect. Due to its elliptical orbit, sometimes the moon is a little closer to the Earth, and sometimes it's a little further away. When the moon is closest, or at perigee, it's a mere 225,300 miles away. When it's at its furthest, or apogee, it's 251,900 miles away.
And fun fact, it is slowly moving further away from us. I think it was like 10 centimeters a year or something. I can't remember, it's been a while. Actually, wait, I can look this up. I'm on a computer. Never mind, I was very off. It's like just under 1.5 inches or 3.78 centimeters. But imagine that, planetary mechanics, it's complicated.
These values are approximations. I've seen different estimates thrown around, but the bottom line is that 26,000-ish mile difference is enough to make the moon look 25% bigger and brighter when it's in its super form. But it also has an impact on eclipses. The moon's apparent size from the Earth is just big enough to perfectly cover the disk of the sun during a total solar eclipse, which is a hell of a serendipitous coincidence, right?
Yeah, exactly.
But what happens if that happens when the moon is closer to its apogee? The moon's fluctuating distance from the Earth means its diameter can appear up to 12% smaller than its maximum, and if it's small enough, it can't completely cover the sun, leaving a burning bright ring of sun visible instead of just the sun's outer corona.
Yeah, which would make it, much harder to look at.
This kind of eclipse is called the Ring of Fire.
Wonderful.
On October 14th, 2023, 8:05 a.m. Pacific Time, the cosmic spheres will begin to align in Saros cycle series 134, and annular eclipse with the moon only 5 days after its apogee. The last eclipse of this Saros series occurred on October 3rd, 2005, an annular ring of fire visible from the Iberian Peninsula and a swath of northeastern Africa. This year, one Saros later, the moon's shadow will trace a similar path, but it's starting 8 hours later, from just off the west coast of the northern United States.
Wow, going through that traveled a long way through Central America before it started moving. Wow, that was almost perfect. That was weird.
On October 12th, about 5:30-ish p.m. Pacific Time, I also enter the cosmic alignment when I roll up on the city of Eugene, Oregon, population 176,654, and me. Eugene is just south of the upper edge of the eclipse path, which means it'll be solidly located under the moon's shadow, which will then travel southeast from Eugene across a good swath of the southwestern United States. The moon's shadow will reach Corpus Christi, Texas around 20 minutes later before sliding off into the Gulf of Mexico and then tracing its way through Central and South America. Here in Eugene, we'll have a couple hours of partial eclipse where the moon is obscuring the sun, but the window of totality is very narrow. We're going to have just under 4 minutes.
I wanted to explain how we're going to be looking at the sun.
Accompanying me on this perilous adventure is my trusty travel telescope, through which I hope to capture beautiful footage of a potential once-in-a-lifetime event and hopefully not burn a hole in my phone in the process.
Yeah, that's the one thing, because usually when you're looking at eclipses, you get those special sunglasses, or I've seen other ones where you get a box, you poke a pinhole through it, and you have something projecting the light on it so that you can see the light from the eclipse project on the back. I've never understood people who want to do it through a telescope, merely because telescopes are kind of designed to magnify and focus light onto a very small area, and yeah, for a camera or an eyeball, that's kind of a not a good thing to do.
This we aren't going to use, obviously, but we are going to use something that looks a lot like it, for the crucial reason that we're going to be pointing this at the sun. And if you will observe the warning label that is so important, it comes on the outside of the bag.
It says don't point at the sun.
This is a solar filter. As you can see, there's a very reflective surface on it, and on the back side, it looks like it's completely black.
Never mind, I was not aware that was a thing. Ignore my previous statement.
This is the level of filtration you need in order to safely point a magnifying device at
the sun. Yeah.
Ta-da! You will not be able to see anything through this except for the sun. If we use maximum zoom, we're going to need to keep readjusting the telescope. This is not one of those like telescopes that can re-aim itself for your privilege. Like it doesn't work like that. This thing I have to like manually move.
Oh, of course,
it's
yeah.
surprisingly hard to find things with it. And the farther we zoom in, the more we're going to have to move it. So minimal zoom, which means we're going to be using one of these two.
Cool.
So these are the two. This is a 10 millimeter. This is a 20 millimeter. And I don't remember which of them magnifies more.
I would think the 20 millimeter, just because, you know, bigger number. I don't know. I don't know telescopes. Oh, you know, this telescope thing looking at planetary and interstellar objects. This just reminded me of something. I've never personally seen an eclipse, but I have used like a telescope and stuff. I remember. Oh God, how young was I? I was pretty young. I was still a yellow tie in Scouts at the time. But we were going to like this big scouting jamboree at a campsite called Camp Goodyear, and well, one, the camp was the camping at the very least sucked because we were in the middle of an open field, and our group, used to camping in the woods, had no sun protection, so that sucked. But this is neither here nor there. During the night, they had like 3 telescopes set up, and they had one pointed at Venus, Jupiter, and Saturn. And I actually got to look at all 3 of them, and I still remember that. That was so cool, actually being able to see like Saturn. No, yeah, it was Saturn with like the rings. It was so cool. I mean, granted, like they did have to like, you know, keep readjusting it every couple of minutes just because, you know, the Earth and everything else moves. But it was still so cool. I wish I could do that again. But those telescopes, they were as big as me at when I was at that age. I really gotta try to find something like that again.
One of them magnifies further than the other. I think it's this one, so we're going to be using this one.
It isn't,
Considering
okay.
the fact that the universe seems to basically be an explosion, it's pretty rare for anything astronomy-based to feel like it's moving fast. Short-lived stars have lifetimes measured in millions of years. The progression of the orbits of the other planets in our solar system, the part of the night sky most prone to visibly change, are observed on the scale of weeks or months minimum. The moon is the celestial body that changes the most and the fastest, but on any given night, it's very unlikely that you'll see any movement in the sky that isn't just the slow turning of the Earth, or the occasional shooting star burning up in the atmosphere. A solar eclipse is one of the only times we can actually get a feel for how fast some of these things are really moving. Perceived speed is all relative to size and distance, and everything in space is so ponderously vast and so incomprehensibly far away from us that we see it moving slow if we recognize that it's moving at all. But the moon is whizzing around at over 2,000 miles an hour, and when we have the position of the sun to compare it to, we can see, just a little bit, how much precision is involved in making a solar eclipse, and how much minutes and even seconds can matter, even on a planetary scale.
Well, that's also the thing, like, I've heard some people say, it's like, oh, how can Earth, like, be moving at, how fast is the Earth moving? Yeah, so the Earth is moving 67,000 miles an hour, or 18.5 miles a second. And I've heard this thing before, it's like, oh, if it was moving that fast, I'd feel it. No, you won't. It's like in a car. If you floor the gas in the car, of course you're going to feel the acceleration, but after a while, all of you will be moving at the same speed as the car and you stop feeling it. But it's the same thing with the Earth. You've been moving that fast since the second you were conceived. Of course you're not going to feel it.
While the path of totality is fairly small and will have a very narrow window, the margin of error for the moon partially obscuring the sun is a lot more generous.
Oh, no, yes.
The partial eclipse will be visible from almost everywhere in the United States, Canada, Mexico, and a good chunk of South America. It's going to look like the sun has a bite taken out of it.
And yet somehow I still didn't notice. I did not know this was happening. Though also I don't watch the news that much anymore, so that might be why. I mean, Philip DeFranco didn't talk about it, so.
But here in Eugene, directly under the path of totality in the shadow of the moon, we're gonna see a proper ring of fire. Hopefully.
There's one other factor
There's
that
always
come up in our discussion of orbits and the sun and the moon and
clouds,
relative apparent diameters and perigee and apogee. 'Cause, you know, the moon is 67,000 miles an hour, and the sun is 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, it would be 18.5 miles an hour. So, if we were to look at the sun, and that's the weather. Weather is a chaotic process. Everybody knows that you can't predict the weather more than like a few days in advance. You can get a general gist for like what it's probably gonna look like, but you cannot accurately predict the weather more than like 2 days in advance. We're on the West Coast. It's October. The leaves are changing. It's cloudy. It's cloudy a lot. And if we're very, very lucky, that's not going to be a problem. Sometimes when it's cloudy, you can actually see the disk of the sun when normally it's too bright for you to be able to see it with your own eyes.
Yeah.
So, even if it's cloudy, we might still be fine.
Might be. Oh, look at that. Is it raining?
The day of the eclipse dawns nice and slow, by which I mean dawn is still a few hours off by the time I wake up. I assemble my tools and fortify myself
because you need
for
to
the
get
journey
there.
ahead.
Eugene doesn't have any conveniently located breakfast places within walking distance that are open at this hour, so I'm having this remarkably disgusting sandwich cookie thing.
The 6 a.m. hike up to Skinner Butt Lookout is nice and quiet, and the sky
Skinner
is
Butt?
promisingly
Okay.
clear the whole way up. I reach the summit, pick an east-facing spot, assemble my telescope, and settle in to wait. Unsurprisingly, despite being the first person on the scene, I am not the only one in Eugene looking to see some cosmic spheres align. The lookout gradually fills up with various onlookers, photographers, a couple news guys, and a surprising number of very cute dogs, plus one cat on a leash. I'd show you, but filming strangers is weird and rude, so you're just gonna have to trust me. And as the sky brightens and sunrise approaches, one thought unites us all on that cold, forested summit.
Not the clouds!
Is it looking cloudy to anyone else?
Yeah.
Nightmare of nightmares. A little post-sunrise cloudiness is normal in a mountainous area, but as the time ticks on and the sun theoretically climbs higher, the skies only get more obstinately gray. 8:05 comes and goes, the official start of the partial eclipse, and none of us can see anything. All we have to enjoy is the gorgeous postcard panoply of Oregon's misty forested mountains, and I can see that whenever I want. Time ticks on. Glimpses of the sun occasionally brighten patches of cloud, but never enough to see anything, and it's not long before even us tripod havers lose track of where to point the scope. To make matters worse, normally as the sun climbs higher, it cuts through those early morning clouds, but with the moon cutting its efficacy down to a fraction of its full strength, the daylight is only operating at half power today. The clouds are thick, the sun is a bare theoretical, and a lot of people are waiting to see how disappointed they're gonna be. Not me though, I'm totally cool and for sure wouldn't cry even a little bit. Just under an hour
of
after
course,
the partial
sure you
eclipse
would.
began, at 9:03, I managed to catch a glimpse of a shape in the clouds that isn't moving with the wind. It is my first look at the sun since yesterday. The moon is only 12 minutes away from a nuller totality. The sun is already a narrow crescent. We do not have much time. But the glimpse of the partial eclipse through the clouds is enough to shift the mood on the lookout. Sure, we might not get a clear shot, but we can see some of it. It's cool. It's sad that we can't see it better, but it's still cool. 8 minutes to totality. The sun looks like the kind of crescent moon you only get in cartoons. The clouds are changing. They've gone from a solid gray wall to a stripy, banded gray mass. The sun slides in and out of view between thin patches of cloud. At 9:09, the sun breaks through the clouds enough that, for the first time all morning, I actually need to use my solar filter. It's gone in 30 seconds, but it was pretty cool that it happened. 9:11, 4 minutes to totality. The clouds form a curtain, and the curtain gets darker. I optimistically begin a time-lapse video, hoping to see the moon slide into perfect alignment, only to watch in horror as my beautifully framed-up shot gets consumed in a wave of more clouds.
Oh, no.
It's 9:15 a.m., the start of totality. The moon will be perfectly in line with the sun for the next 3 minutes and 49 seconds, and I can't see any of it.
Oh,
2
great.
minutes later, a miracle happens. A patch of cloud thins out just enough that the sun shines through, clear as day but perfectly dimmed by the clouds to need no solar filter. The ring of fire blazes through in its entirety, and it is beautiful.
Oh, that's awesome.
In a total solar eclipse, the last moments before the moon entirely eclipses the sun and the first moment it slides out of alignment produce an effect called a diamond ring, where a single concentrated burst of sunlight peaks around the lunar silhouette, looking like an impossibly radiant diamond set in a luminous band. An annular ring of fire eclipse will generally not produce a diamond ring effect, because too much of the sun's light is still visible around the edge of the moon.
But the clouds.
However, this time, as I watch, the modeling effect of the clouds passing in front of the eclipse produces something very similar to the diamond ring. The very thing that threatened to make this entire journey fruitless has made the effect all the more spectacular.
Awesome. This
10
is
minutes
so
later,
cool.
well post-totality, the crescent sun slides into an even thicker cloud bank and disappears for good to finish off the eclipse undisturbed.
Oh, wonderful.
We did it.
The Ring of Fire is done. This Saros series won't recur for another 18 years. The Earth and Moon will spend that time wobbling into and out of eclipse alignment in dozens of different ways, producing partial and total eclipses of all shapes and sizes. Solar eclipses are unlikely for so many reasons. The Moon needs to hit the perfect intersection of its own orbit, the Earth's orbit, and our alignment with the Sun. The shadow needs to hit the part of the Earth's surface we're observing from. The weather in that spot needs to cooperate.
Thanks, Eugene. Love you too.
And even beyond that, the fact that the Moon and the Sun appear to be the same size from the Earth's surface is incredibly unique, and without that, we wouldn't get the striking effect of totality.
Oh,
if
no,
the Moon
yeah.
were further away and appeared smaller, every eclipse
Oh,
would be in
Phobos,
a
yeah,
ring
of course.
fire. Or even something less impressive, like the transits of Mercury in front of the Sun, barely a blip on the radar. And if the Moon looked bigger, it would blot out the Sun completely with none of the effects of totality. No visibility in the corona, no diamond ring, no ring of fire. Earth's moon is the 5th largest moon in the solar system, and the 4 frontrunners that beat it are all orbiting Jupiter. By moon standards, compared to the size of the Earth, the moon is absolutely massive. We're more like a binary planet system. But the moon is also moving away from the Earth. Current estimates suggest that back in the Precambrian era, 2.5 billion years ago, the moon was only 205,000 miles away, 20,000 miles closer, with a correspondingly higher apparent diameter. And the current theory of its formation suggests that when it first formed from a cataclysmic impact on the proto-Earth 4.5 billion years ago, the newly forming moon was orbiting only 15,000 miles away, with an angular diameter of about 7.5 degrees, 15 times more than its current 0.5 degrees. Currently, due to tidal
Absolutely
shenanigans,
nuts.
the moon's orbit is widening by about 38 millimeters per year. It'll be a long time before it has any visible effect, on the order of billions of years, but on an astronomical scale, it highlights that the current arrangement is temporary. Solar eclipses as we experience them are not an immutable component of the universe, or even of our planet. We exist on a cosmic scale, in a narrow slice of time where the arrangement of our solar system allows for this spectacular event twice a year. We're lucky enough that it happens. Throw in how lucky we are to see it, to understand how it's happening and what it means. We don't live our lives on a planetary timescale. The bulk of the universe moves imperceptibly slowly from our perspective. Without a reference point, the movement of the moon doesn't feel fast. A solar eclipse, an event of such monumental precision and briefness, is one of the only events that lets us actually perceive the movement of the universe, to actually
Absolutely
feel what
nuts.
it means to be falling through space. So, if you have a chance, I recommend seeing if you can catch the next one. April 8th, 2024, one eclipse season from now, we'll see a proper total eclipse passing over Mexico, the eastern United States, and a slice of Canada. This
Of course, it's going to be going right over Lake Ontario, so I'm going to have to, like, go somewhere else. Great.
This one is part of Saros Series 139, which, fun fact, was observed back in 1898 by 2 separate expeditions in India, one of which was done and documented
Cool.
extensively by astrophysicist and observatory director Kavasji Negambala, who 2 years earlier in 1896 had joined a large British expedition to Norway to observe a solar eclipse from Saros Series 124 that was completely obscured by inclement Norwegian weather. I'm not gonna lie,
Of
this is the
course.
only part of this whole adventure that, like, nearly moved me to tears. Not because I'm sad. He got to see an ass-kicking eclipse 2 years later and documented the hell out of it, just because when I read those words, the camaraderie I felt with this man was unbelievable. It's kind of beautiful that my
course.
dumb weather sabotage travel plans are part of a grand chain of human tradition binding me through hundreds of years of people who want to look at the cool space thing. Anyway, the 2024 eclipse is not a nuller. It's going to be proper totality with the corona and the diamond ring and everything, and the path of the moon shadow is going to cover a good stretch of North America. A partial eclipse will be visible from most of the US, but if you can get under the path of totality, I think it'd be worth it. Okay, now that that's out of my
Cool.
system, back to my regularly scheduled obsessions. Tune in on Friday for a very normal video from Blue, and a couple weeks from now for a much more normal video from me. Alright,
Oh, okay,
peace out
wonderful.
everybody, and always wear your eclipse glasses. Don't stare directly at the sun. And also, don't point your telescope directly at the sun without a proper solar filter. Okay, bye.
Oh, God. Ugh. So, yeah, again, it's just... I've never seen one. I think there was a chance where we could, where we were close to one when I was younger, but we didn't have the proper stuff to, like, really look at it. Like, for some reason, we couldn't find any of those, solar glasses in time or anything, so, I remember I tried looking at it through, like, through my DS camera, and it didn't work in the slightest. Oh, yeah, it's absolutely nuts. I mean, the universe is beautiful, even if it is terrifying at the same time. So yeah, original video is linked in the description if you haven't seen it for some reason. Corner video will lead to my Let's Play of the day. And with all that out of the way, I hope you guys liked. If you did, leave a like, subscribe if you have not, and don't look directly at the sun. Goodbye.